This diagram represents the traditional architecture of higher education. For decades, institutions have separated learning into strict vertical silos: design, computer science, mechanical engineering, and electronics. Students picked a single lane and stayed in it. Then came generative AI, a computational systems capable of instantly producing text, code, images, and design drafts from simple prompts. Tasks that used to take days of specialized labor inside these isolated departments can now be generated in seconds. Because AI handles this routine content so rapidly, the economic value of executing a single isolated skill has plummeted. The market no longer pays a premium for raw production. A student can no longer guarantee their career success simply by memorizing the specific rules of one academic domain. While an algorithm can write a block of code or draft a layout, it struggles to frame a complex real-world problem or visualize how different physical and digital systems interact holistically. The value of a human graduate relies on multidisciplinary synthesis, the ability to connect logic, design, and engineering to build functional solutions. Institutional frameworks from organizations like the OECD and the World Economic Forum have identified a new set of priority skills. They emphasize critical thinking, simulation, and cross-domain collaboration over memorization. The primary objective for a modern learner is to take a conceptual idea and turn it into a working, measurable experience. Traditional teaching methods, which rely heavily on static textbook and slide presentations, fail to develop these dynamic abilities. You cannot learn how a complex system behaves by reading a static description of it. To accurately reflect how modern problems are solved, institutes must adapt tools that provide interactive, real-time feedback. The foundational language of future higher education is interactive computation. We can clearly see this shift by looking at a Venn diagram of modern disciplines. Modern digital products are interactive. A designer today must understand computational logic and state changes, how an interface actually responds when a user interacts with it. On the other side, programmers must understand user experience, visual flow, and communication clarity. Software is judged by its usability. A flawless block of code will fail if a confusing layout prevents user from adapting it. In the physical sciences, mechanical and electronics engineering students must test systems using virtual simulation tools before cutting metal. By visually simulating kinematics, the study of motion considering the forces that cause it, engineers eliminate the high costs, risk, and ambiguities of trial and error fabrication. This precise area of overlap is exactly where curriculum developers need to target their resources. Solving real-world problems requires integrating visual design, computational logic, and engineering principles into a single workflow. When institutions look for software to build these workflows, they encounter an administrative bias, the tendency to dismiss real-time engines as gaming toys. That classification ignores the software's architecture. Unity is a hyper-realistic, real-time 3D simulation platform. If we strip away the entertainment label, we reveal core engineering components, physics solvers to calculate gravity, logic compilers to run scripts, and input-output handlers to process data. Unlike pre-rendered animation, Unity compiles the script logic instantly. The environment responds the moment a user interacts. This instant feedback loop is exactly why modern industries use Unity to build digital twins, virtual replicas of physical systems, along with virtual science labs and immersive training simulations. These environments yield measurable data and allow for active exploration, offering a pedagogical advantage over the passive consumption of a standard slide presentation. Educators deploy these simulations across multiple platforms, from desktop computers, mobiles to augmented and virtual reality headsets. Games are one application of engine technology. They are not the definition of it. To teach this multidisciplinary curriculum, institutions require a two-part software stack that handles complex asset creation and real-time interactive logic. The first half of this pipeline is Blender. As seen on the left side of this workflow, Blender handles content creation. Using procedural nodes, students build precise 3D models, apply textures, and design environments. Learning Blender teaches students structured spatial design and procedural thinking. The second half of the pipeline is Unity. Here, visual assets receive measurable physical properties and user interactivity. This specific pipeline forces students to connect creative visual communication with hard computational logic. The relationship is symbiotic. Blender creates the world and Unity makes the world behave. This theoretical pipeline maps to concrete academic outcomes across diverse departments. In mechanical engineering, students export a machine model from Blender and simulate its precise motion and assembly sequences in Unity. This engineering workflow allows for rapid iterative prototyping without consuming physical materials. In electronics and embedded systems, students visualize the hardware device in Blender, then simulate the control panel data logic in Unity. Architecture department move past static 2D blueprints, transitioning into fully explorable VR environments that accurately simulate lighting and structural interaction. In education and pedagogy programs, future teachers learn to build interactive concept models rather than relying on flat textbooks to explain complex subjects. These are active workflows currently demanded by industry research labs. Mastering this pipeline gives students the ability to simulate, test, and prove a complex system completely before it exists in the physical world. This chart tracks projections from the World Economic Forum's Future of Jobs Report 2025 alongside OECD data. It shows steep upward trend lines for analytical thinking, technological literacy, and design. Technological literacy and interdisciplinary analytical thinking are the fastest growing demands globally. Universities that continue to output narrow domain specialists are actively misaligning with global economic demand. Adapting tools like Blender and Unity moves the curriculum beyond technical software usage and towards systemic solution building. These platforms provide a language for building, visualizing, and communicating ideas through interactive simulation. A future-ready institution prepares its students to build connected experiences rather than submit isolated assignments. By utilizing simulation to fuse human creativity with computational behavior, institutions directly address the complexity of the post-AI workforce.